You've come to Life of a Raindrop. So it's basically, I've created this presentation and I'm just going to take you through what happens to water. So where does it come from? Obviously, we kind of all know that. We've learned that from geography when we're at school. But where does it go when it hits the ground, when it enters a proprietary system? Or if it hits a hard landscape, or where it's going to go in terms of, is it going to connect to a combined sewer? What kind of energy is it going to need when it gets there? Or does it connect to a piece of green infrastructure or a river basin or something of that nature? So obviously we are a manufacturer per se, but I've made this as CPD orientated as I can. So there will be a few images of product in there, but it will be orientated around CPD. So where I'm from, so my name is Adam Kane. I'm a regional specification manager for ACCO. I am actually a civil engineer, so a qualified civil engineer. I've been qualified for like 8 years now, I suppose. I'm that old. So I've been in the field for quite a long time. I originated from local council. I was a bridge engineer. Then I did something to do with FEA software, and then eventually I moved on to the dark side, and now I work for a manufacturer. But I still do a lot of the technical stuff where I support engineers on the road. So if any of you are from the south, anybody from the south of the UK? One from the south? All right, brilliant. So if you need any support, just give me a call. And if any of you want my card after this, if I do impress you enough, then of course come and collect a card from me. So what we're going to go through today, well, first of all, we're just going to focus on the cycle, so the hydrological cycle first and foremost, and then we're going to look at some of the drivers and what actually happens to water as it hits the ground, and primarily focusing on the highway and what negative effects it could have. Then we'll look at a bit of the treatment trains. This is kind of the mantra of ACCO, which is collect, clean, hold, release, but it will feature a lot of SUDs in there as well. And then we'll look at how we can integrate our SUDs into our network. So this is really talking about where we're going in the future and what codes of practice we might follow. So some of you might have designed these into your systems, and those who are drainage engineers, and some of you might just want to understand of how we actually design SUDs. And then we'll look at intelligent systems, the Internet of Things, and how we've got the continuous monitoring and how we might maintain and manage our systems in the future to make them, one, more economically viable, and also to make them more efficient, so we can find out when we do need to carry out maintenance and things like that. And then finally, we'll just do a little bit of a focus on maintenance. So first of all, you've all seen it, you all know it. So it's the water cycle, or the natural water cycle. So really the key things are evaporation, you've got evapotranspiration from plants, and then you've also got condensation and rainfall happening at the end of the process. So we all kind of know this, so we know what happens. But what generally happens is in these situations is as it lands on a greenfield situation or a meadow or something of that nature, a forest, then generally it will just infiltrate into the ground. And then that water creates groundwater flow. It also purifies it through the process. And as it gets carried away, it goes into the water basin or the river basin. And that creates a constant flow throughout the year, which is really important for biodiversity and natural systems. Without water, no natural systems could survive. So what generally happens is we become more urban and we create our urban environments. We start concreting over everything. We make them impermeable. So in making things impermeable, obviously there's less infiltration into the ground, and therefore there's less flow going to our river basins, and therefore over a period of time they become dried out, which is what happens in villages across the country. And quite often, because of that high level of impermeability, as the water hits the ground, then there's an acceleration of that water as it cascades off the surface. So if it's not being able to infiltrate into the ground or evaporate straight off the surface or evapotranspirate through plants when they soak them through their root systems, then it's literally going to just cascade straight off the surface, and eventually that creates a problem downstream. So if it's impermeable, fast-flowing water, no restriction to it as it comes from a site, then whoever's downstream of that area, and we've seen this up in Yorkshire at the moment in terms of the flooding that's happening up there, the low-lying land is the area that gets hit the worst, because all of the flow of water just cascades straight towards that point, and then you get an elevated level of water, i.e. there's flooding in that area. We'll discuss that in a lot more detail as I go throughout the presentation, but this is just a basic scope of it as you go from the natural system all the way through to a heavily urbanized industrial environment, and you can see that the runoff increases, you get a decrease in infiltration, and quite often or not, you get a decrease in the evapotranspiration through plants, which is what you see there. So one of these problems of urbanization is population growth. So what you see here is a graphic where over 5% You're going to see over a 5% increase in population up until 2022 for 8 of the 13 regions of the UK, and none of them are seeing negative. So what that's going to mean is that more people are flooding to urban areas, and therefore it's going to cause more housing, more impermeable surfaces, more often than not anyway, and they're just trying to find that balance. The other one is about economics and showing that why people are moving to urban areas, and that's just because simply there's more highly skilled jobs and higher pay in those areas. And this is when we're talking about urbanization and we're talking about land use. This is the Coordination of Information on the Environment, or CORIN for short. And what this is where they've used data from photography and taken planes over a landscape over the whole of the UK, and they've taken imagery and analysed the actual land use in its current state. And they originally took it in 2006 and they did it again in 2012. And what they found that 2,250 square kilometres had changed in that 6-year period. Now, that doesn't mean it's all made into an impermeable surface. That could be it's from forestry to commercial, from commercial to housing, that kind of, it's those small changes that happen. But if we said that in a 6-year period, 1% change, and if it is 2,250 square kilometres, if 10 millimetres of rainfall landed on that area and it was impermeable, that'd be enough drinking water for 2.5 days for 60 million people. So when we talk about our systems, our sewer systems, and how it all connects together, and the fact that most of our stuff goes into a combined sewer network or a foul sewer network, and all that has to go to a water treatment plant, and if the water treatment plant can't cope with it, then eventually it enters our natural system. So the idea is that we use more of it on site, and that will be a characteristic of this presentation. And that's just those red dots illustrate an area of more than 1 square kilometre that's changed in any given period over that 6 years. So going on to the road network, well, I don't know how many people enjoyed traffic on the way here today. I didn't, I took the train. But the fact is that we are seeing an increase in road users. There's over 33.6 million licenses held in the UK. So that's the number of people that can drive, and we've got a population of 70 million people, so just less than half or something of that nature of people that can actually drive in the UK, which is crazy. There's 37.8 million vehicles, so obviously people drive to work and then they drive another vehicle while they're at work, hence that's why there's more. And of that mix then, I think it's 80% of those are cars and 11.7% are just light goods vehicles, and then it drops down from that, and the rest of the 10% make up of basically motorbikes, of heavy goods vehicles and things of that nature. Of that split, 60% of that is petrol and 40% of it is diesel, or 59 is petrol and 40% is diesel, and the other 1% is gas, electric, those kinds of things. So, and of that, so the graphic you see here is the number of miles that have been travelled in the UK, and there were 327 billion miles travelled in the UK in 2017. So that's billion. So it's quite a considerable number of transport miles on our road network. So you can see how it's under capacity, or it is getting to a critical mass of capacity. So of this then, so that was an increase of 1.3% on the year of 2016. So of this van journeys, I'm focused on van journeys and car journeys. Van journeys increased by 3% and car journeys increased only by 1%. Public transport decreased by 3% in that time. So, and I know this is all about the life of the Raindrop, but as we're adding more and more cars to our network, then obviously that's going to add more pollution unless we focus on having electric vehicles or hydrogen-powered vehicles, or if we're having more public transport. So that's the reason why I'm focusing on that. And particularly it's about when we talk about congestion as well, so as more cars are added and we see our journey time is elongated, so there was an increase of 9 seconds for major roads, and that's only a 1.1% increase, but still. And then the journey time increased for 46.9 seconds for our urban roads. So that's for an A class, and that is adding on. So say if you had a a road which was completely free of traffic and then compared it to a journey time when you actually had traffic, then that's the amount of journey seconds that have been added. So that 9 seconds, so if the motorway is completely clear, then it would be 9 seconds less than the journey you took on the motorway as you made your way up here. Does that make sense? Hopefully. And then if on the urban roads, it was 46.6% or 46.9 seconds. So all this, as I mentioned, adds to pollution on the highway. So what you see here, so transport is now the largest contributor of greenhouse gases in the UK. So it's gone ahead of energy now. So that's a critical mass or the tipping point was a couple of years ago as we switched to more gas turbines. So yeah, the road network produces more. We've seen a 65% increase in the amount of pollution that's produced by light goods vehicles, and that's because diesel was massively promoted under the Labour government, and until recently they found that obviously that's massively poisonous with the nitrous oxide that is produced out of the exhaust pipes. Excuse me. But we have seen a decrease in the car outputs in terms of the level of pollution that's produced there. So that is a decrease on that front. So this is just a side note, and this is the health implications of pollution in the UK. So the pollution directly contributed to a cost of 1.69 billion to the NHS and social care system between it's going to be between 2017 and 2025, so that's predicted. And it cost our economy 2.7 billion in terms of the overall cost of dealing with problems that are actually of people taking days off and things of that nature. So it is a massive contributing factor to our everyday lives and also our economy in terms of the level of pollution. And recently there have been articles coming out in The Guardian of how this is going to affect our young people's healths in the future as well as we have more climate change and things of that nature. So there have been commitments to lowering the effects of pollution. And this has meant the progressive nature of going over to more electric cars and hydrogen-powered cars. We've only seen an increase from 0.9% to 1.7% of the vehicle use since in 2 years, but still that's an increase of 1% or 0.7%, which isn't too bad, but we just need to accelerate that program. The image in the bottom corner here is actually a pilot scheme. It's happening in Southampton. I don't know if many of you have seen it, but they've started adapting the vehicles so they've got a filter on the roof to reduce and remove the levels of air pollution in the environment. So that extracts it, which is ironic considering it's a diesel vehicle. So here's a bit about the danger. So as it falls, it lands on our road network, it creates a danger. So what you see here is on the motorway is reduced visibility, so that's people you can see and people that see you, so therefore it creates a bit of a danger. It also affects your stopping distance and thinking time. Aquaplaning and flooding create a problem for vehicle performance and also the vehicle control, so that creates a danger. You've got pedestrian safety. It is actually illegal to splash somebody if you did it on purpose. I don't know how they would actually prosecute you, because you could say it's an accident, you didn't see it, but obviously it is a danger. So making sure you design appropriate drainage and also maintenance schemes into your products will make sure that people aren't splashed on the highway. It also presents another danger when you do have flooding for pedestrians, because they might make their way into the highway to avoid that flooded area, and therefore they put themselves in danger. So all these have a problem. Black ice also comes into that, and snow comes into that in terms of the dangers they cause, especially black ice when you can't see it, and of course you could skid and come out of control in your vehicle. And finally, the bottom image down there is climate change. So all of these different things are exacerbated by climate change as storms get more aggressive over time. So it is going to be a massive problem, and it is going to have an effect on our environment, including the heating effect as well. So that's going to have a massive effect on our road network and our maintenance requirements and what effect it has on the materials that we use in those situations. So here we're just talking briefly about a proprietary product treatment train. I'm going to talk about SUDS, and some of the SUDS are listed down below. So this is Collect, Clean, Hold, Release, which I'm going to go into a bit more detail in a moment. So what you can see are different avenues of actually controlling the water. So basically we have to collect it as it lands. Then if it isn't polluted, we might be able to just put that straight into a natural system. If it is, we might have to go into cleaning it. So we might have to use oil separators, heavy metal separators. We might have to use a type of SUD system, so a piece of green infrastructure to do the work for us. Or we could just force it all the way down to the treatment in terms of the water treatment plant. You have to attenuate the water on a site. So given capacity issues with the network, it's becoming close to being under capacity. So what we do in a sense, just for people that don't understand it in the room, we have to regulate the flow rate coming from a site. So what we do is that at the end, when we come to release, we have to control the flow. And of course, when you put a stop cork on the end of something or you reduce the flow of something, then it backs up into the system, and therefore you have to store that water on the site itself. So many different methods. We're showing GSA as storage systems on the actual the slide there, but we will go into a bit about SUDs as well. And then finally, we can release it into the natural environment or into the combined sewer. So when I said about connecting to the sewer network, we might want to restrict the flow to make sure they can clean the water and make sure they're not using as much energy, or it doesn't cause issues downstream in terms of flooding. So we're going to go through them one by one and try and stick as much as we can onto the highway situation. So first of all, just talking about collect in terms of how you do it. So in the slide before, you may have seen that there's loads of different methods of doing that. So it could be a filter drain at the side of a road. It could be a gully system. You will, if you live in Birmingham, you will actually recognize this project or scheme. So this is the central reservation, and what happened in it, I'll explain, I was just going to do it about collecting, but what happened there is that one of the gratings was left up. It was about 25 years ago, what it says there. But it was a grating was left up and it caused a motor vehicle accident. So from this point, what actually happened is that on any highway scheme in the UK now, you have to use something called a monolithic type system. And that means it's just a one-piece unit, so you don't endanger people's lives. So what actually happened is that in this scheme, then it got changed over to a monolithic type product, and therefore it made it safe for any road user. So that's what's actually happening. What I was trying to highlight on the slide is that no matter where it is, you have to actually collect the water. So you can see this is quite an industrialized area. There's no green infrastructure on either side of the road, so it's outletting straight into the middle, and it's actually conveying the water away. So channels are a good way of affording that. Gullies and other items or proprietary products can do the same in terms of catching water. So that is it when you talk about monolithic type things and making sure that you collect it. They all do the same thing. They all catch water. It's just about considering what loading it has to be under and what design criteria you have to follow as well. So what I was meant to highlight on there is that when you're carrying out a design in terms of how much water is caught on the ground, you have to design it for, in the highway situation, to a 1 in 5 year storm. Now, some schemes or highways authorities or indeed local authorities will stipulate you have to use a higher storm. It's entirely down to them. But in terms of guidance and national guidance, which is the design manual for roads and bridges, they give you a number which is 1 in 5 years, with a caveat that it has to take account of 20% climate change. So just have to make sure you design that into your schemes. So that's that. And in a highway, that has to reach a minimum of D400 loading as well. So in order for it to sit in the highway. Unfortunately, I can't go into too much detail. I've got 20 minutes, but there are categories of loading that you have to adhere to for any system you put into a highway situation. So whether it be a gully, it'll have to be D400 loading, or a channel will have to be D400 loading, okay? And that's talking about monolithic systems. The one thing to highlight is the opening at the top. Each one will be different depending on the situation you face, and depends on what you perceive to be the potential level of debris that might be going in there, or how fast you want the water to actually enter the system, so you know these are bigger than the other ones going on. And you'll see these everywhere, or you see in quite a large array of the environment, is a combined curb drainage type system. So what you see is that these are a good conveyance tool of allowing the water to cascade into the actual channel at the side of the road in order to convey it away. The reason why I'm highlighting this, but you want to stop, in order to stop aquaplaning, ponding, localized flooding, is to create a long conveyance path. And in that long conveyance path allows it for the water to discharge a lot quicker. So what you see here is the connectivity up to different SUDS environments. The reason why that's highlighted is that what epitomizes SUDS is making sure you keep things as high up on the site as possible and use it at the source. Now, one way of saving space and keeping things high up on the surface is if you have a high outlet into a green piece of infrastructure. Car parking spaces, I mean, we're talking about a highway here, but car parking spaces are worth £2,500 a week to a supermarket. So in terms of context then, if you can shrink in the sides of any green infrastructure which needs a 1 in 6 crossfall for safety so you can crawl out of it, it's beneficial to try and keep things high up on the site. So imagine if we replace that and we have to have a pipe has to be buried 1.2 meters to the crown, therefore your swell goes from being 600 millimeters down to, well, 1.6 meters, so which is quite a considerable distance. But what we're talking about here is the guidance for oil separators and the SUDS guidance in terms of whatever we want to design as SUDS. So first of all, just talking about proprietary products in terms of oil separators are devices that remove oil, and I'll explain those in a minute, but that's the guidance you follow. And then the SUDS manual has something called the mitigation indices. Is there anybody in this room that is designed to the mitigation indices that have come across them? Thank you, that's one individual. Has anybody else seen it, or you have? So within this are tables in the SUDS manual. So what they do is have a table for the location you're working on. So in this case, we'll say a road. So say if we said it was a trunk road, we might say it's got heavy loading. And what it means by heavy loading is it's got heavy loadings of these 3 things, which are hydrocarbons, heavy metals, and total suspended solids. And what we have to do by using tables and design is we have to use a piece of green infrastructure or a proprietary product to mitigate against these levels of pollution. So that's what essentially we do in practice, and I'll explain a bit more about flow rates and stuff coming out of a system. So these are proprietary products in terms of oil separators. What you see at the top here that's an oil separator, that's a heavy metal separator. I'll explain them one by one. An oil separator is a device that removes the oils. It does this by gravity, so you get total suspended solids separate and go down to the bottom, and then you have oils which just float to the top. Oil floats on water, and then it's got a little gate on it that closes. Now, essentially that's removing 2 of the pollutants from our 3 that we mentioned a moment ago. And there's 2 different kinds. So you've got full retention. These come in a range of different sizes. They can go absolutely massive, and they have a range of different layouts. But in this case, we've got a full retention and bypass. Full retention treats every single bit of pollution coming off the site, or every single bit of water. And then you've got the bypass, and it only treats the first 10% of the water. The idea behind that is the first 10% of rainfall will have the highest concentration of pollutants, and therefore if you can clean that, then you are kind of doing most of the work, and then the rest of it will go to a combined system. You never really use these in combination with SUDS unless they're actually doing a large volume of the work. So, and you've got different classes. So you've got class 1 and a class 2. Class 1, you'll hit 5 milliliters of oil per liter, or in a class 2 is 100 milliliters of oil per liter. So it's about what they allow to be carried forward. In the bottom, I better speed up, is a heavy metal separator. Now what this does is it removes all 3 of them to a high degree. It's a very specialized item, but it uses gravity to remove the pollutants is in total suspended solids, and then it's got a filter inside it which removes the heavy metals and hits a high degree of them in terms of 0.8, 0.8, and 0.8 for those who in the room who do understand. But the idea is to try and find or strike a balance between maybe proprietary products doing a lot of the work for you, and then actually having green infrastructure that can do essentially the amenity and biodiversity work for you at the end of a scheme. And here are just some of the SUDS features that are available to put by the side of the highway, or not in case of the green roof. But for the rest of them, they can be put by the side of the highway in an environment. So each one of these hits a different mitigation indices, and it's all described to you in a table, and you can use them in sync with each other, so you can actually have a chain that's created going from one to the other. They carry out their treatment with flow, and you actually have to monitor the flow going throughout the actual device and the amount of time it takes to get from one end to another. So I'm only going to focus on a swale in this particular presentation, but what they recommend is that the flow should be 0.3 litres a second in the swale. It should be no more than 100 millimetres in height, so that means you have to change the width of the swale and the length of the swale to suit the design that you're working with, and it must take at least 9 minutes for water to travel from one end of the swale to the other end of the swale. So that's essentially what happens. And if it's got multiple inlets, it's got to take 18 minutes to go from one end to the other end. So basically what it's doing is taking account of the length of time going along the swale itself is actually purifying the water. So you might be limited on the space you have on a site, therefore you might want to shrink the swale down. So kind of finding that balance between an underground system and above ground system. And they are designed to a 1 in 1 year event. So you're only really dealing with the pollution for a 1 in 1 year, so it's really dealing with that flow in the base. But you might have to go up to the storing of water within a piece of green infrastructure up to the 1 in 100 year period. Well, it depends if you're working on a highway, it might only be the 1 in 5 plus 20%, but if you're dealing with other environments, it could go up to a 1 in 100 year storm. Okay, and now going on to hold. So really, this is what we were talking about before in terms of the pressure on the sewer system. So this might be, well, the Greenfield Response. So here we go, we've got a lovely green meadow which is completely undeveloped. There's no hard surfacing or impermeable surface on the whole site. The water is actually just a nice little peak, a nice little bell curve as it were. So that's the number of litres of flow over the time. So that's the response to the actual rainfall events coming down. And then if we were to come along and we were to concrete over the whole of the area, you're going to see more of a flow like this in terms of you're going to see a massive peak or influx of water on the site because it's all having to flow, it's all going to flow off rather quickly. And of course, if you compare it as in what the water treatment facility might have to do or the natural system might have to do, it might only have to treat this much water for this period of time, but now it's had to treat it a lot quicker and a lot higher volume. And of course, if we've got a multitude of different sites, so these are 5 different sites on a network, as you can see the network here coming up, all of them are eventually going to discharge at a downstream point, which is P. Now, if P is a low-lying area, let's say it's a small village, you've got loads of villages connecting up above, then potentially that village could flood. If it's the water treatment plant, then there might be the possibility that it can't treat the level of water that's coming into it, so it had to use a combined sewer overflow, and that means it discharges straight into our river network or our stream. I mean, it can be controlled spills, it can discharge that water or hold it on fields and things like that, which you often see when you're going out into rural environments, but sometimes they can't do that and they just have to discharge into the local river, which causes a high level of pollution in some cases. So then it can have a negative effect in terms of if it causes flooding downstream and they sacrifice a village, let's say, that's less popular with the local villagers, then that could potentially happen as well. So a controlled flooded event. But obviously this has a negative effect on our urban environment, but also our natural environment as well with levels of pollution going into it. So water companies are under increasing pressures, we mentioned before, in terms of the capacity of their network. And this more often than not is because of population growth, a lack of investment in the actual sewer system itself. It can also happen in urbanization in terms of the buildings and infrastructure that we're building, but it also is a massive problem is urban creep as well. Now this is where people will create another driveway at the front of their house, or they add a conservatory to the back, and they might not necessarily have a nice little tank or something, and all that adds up to combine to a much larger volume of water that's entering the system. So for this reason, then they've come up with the capital assessment framework, which is a paper and also a calculation has come out from HR Wallingford, who is working with the water companies to work out what capacity is on the network, and effectively they work with councils to give you as a designer the rate of discharge that can go into their sewer network. I mean, it is worth mentioning here that all of this does in some way culminate with our energy use as well. So if I told you that the water industry is the second biggest user of energy in the UK, and the aeration pumps, as in the air pumps that are used for the end of the process, let's say, they take up 1% of the total energy use for the whole of the UK. So that kind of puts into perspective is in, if we do want to mitigate against energy use and climate change and things like that, we do have to make sure that surface water that's falling and being cleaned is just connected straight into green infrastructure. So just talking about infiltration, evaporation, so we kind of touched on it in the start. So infiltration for recharging groundwater flows. What we're showing you on the screen here is actually a GSA storage system that's used for this. So what you see is that you've got, in effect, this is what we use in industry. So you've got infiltration into the ground and you work out surface area and an infiltration coefficient. And then you've got the storage methodology, which is where you've got a controlled outflow from the system, the water's backed up into it, and therefore we've had to store on the site. Obviously that can be done with a variety of different things such as SUDS as well. There's an array of proprietary products on the screen you see there, so different geocellular storage systems, different plated structures at the top right-hand side. You can also have buried pipe systems, concrete box culverts, and SUDS systems as well. So remember, all of these can be interchangeable in terms of what your site has the area for and what you can use. But more often than not, because concrete structures are seen as so expensive, plated structures are seen as awkward, then geocellular storage system, which are basically plastic crates, are stored underground. That's the ACO one in the top left-hand corner. And finally, just to go on to release, and then we'll go on to a few more of the subjects. So what you see here is two release mechanisms. So you've got a Vortex Flow controller against an orifice plate, and there are loads of different methodologies. I'm only going to show you two here, unfortunately, but there are loads of different methods of actually releasing water from the site, including weirs, baffle gates, and stuff like that. So there are different methodologies. So what you see here is the red line is a orifice plate, which is the direct relationship between the head of pressure and the orifice diameter, and then you've got a Vortex Flow controller, which works by trapping a pocket of air in the top. But the idea is that in this, it shows that the Vortex Flow controller releases more of the water from the site. Now, this doesn't really characterize what we're actually aiming for in a sense, but in terms of the ideology behind removing as much water as quickly as you possibly can, it reduces the amount of storage that you actually need on the site itself. So it will be dictated by the environment you're connecting to, though. So combined sewer, obviously we said about the restriction there, but if you are connected into green infrastructure, the flow rate coming out of the system will directly relate to potential scour in the system. So back to the swirl again, I was trying to keep that a reference point, but they don't like it being over 1 meter a second going into the swirl because it could potentially cause scour in the system. I mean, it says 2 liters a second if it's on a slope, but it's 1 if it's not. So it is worth making sure that you're designing that and making sure that you're not releasing too much at any given time. So these are just the two things I was talking about. So you've got the orifice plate there, it's just a header relationship between the orifice, and then that's where the pocket of air sits in the top and it gets knocked out. So when the head reaches a prescribed level, then it will knock that pocket of air out and it creates a vortex like you see in the plug hole as you turn your finger around, and then it controls that flow of water going out. So in a lot of schemes you'll see these being used on them. And finally, in the release section, and we'll move on to SUDS, is the ways of controlling or slowing down the velocity of water and preventing that scour occurring. So these are things called swirl inlets, but the idea is that you are slowing the velocity of the water down to such an extent it doesn't create scour in the actual system. You can see that it's slowed it down quite a bit because you've got all the debris that's on the outlet of it there. So just to talk about SUDS. So SUDS are really important for climate change or mitigating climate change in the future. It's really important for our health as well, in terms of our health and well-being. More green spaces mean healthier people, healthier clean air, healthier environments. So what it really depends on is to create that kind of environment is the 4 pillars of SUDS. So you've got water quality, which we discussed, water quantity, we also discussed that. Then you've got amenity and biodiversity and how you can actually integrate a system to support those different things. So what I'm going to do now is go through into a few little case studies and different things. So what you see here, so the image top left is a soakaway next to a highway. So what you have is just a free fall of the water cascading into the subbase, and that acts as a storage medium, but also to purify the water as well. The image bottom right, should be bottom right, What they've actually got here is it's a swale, but they've got a geosayer storage system underneath. So the swale's doing the body of the work, but anything over that capacity, the geosayer storage system is acting as a storage medium all the way along. So it enables you to actually store a large volume of water over a long distance. And then finally, to protect the nursing home, we're seeing quite a lot of flooding in that area, and they use the geosayer storage system on the other side of the road to prevent that flooding. But again, it's in the verge, and it's the verge actually goes a long way to promoting corridors of life. So it gives an avenue for species to move up and down. Tree pits. Trees are really good in terms of they create shade, prevent against climate change, create oxygen for us. They do suffer from needing or requiring 80% compaction, whereas our highways and the way we can do construction, we want 100% compaction. So what you can use is geosayer storage structures around the base of the actual tree pit itself, and the formation of them will promote the tree bulb to actually, and the root system to grow into the actual geosayer storage tank. That enables it to be prosperous and grow. Here we have an example of a vegetated area. Quite often not, you'll see in car parks and things, the curb will be raised. It's protecting or preventing the highway traffic from mounting the vegetated area, and also for the soil to spill out. But quite often than not, the water can't cascade into the actual system. So therefore, how is it getting any water except for what directly lands on it? So therefore, you have to select hardy plants that don't need much water. They don't promote or support much biodiversity and life. So what you can have is you can have a permeable pipe coming out the back of your gully, channel system, or in this case a raised curb, and therefore the permeable pipe will actually go into the soil and will water it in a sense. What you see here is the same with a gully, and this is actually a planter gully itself that sits in the soil, and you can set the holes at a higher level. So what you can have is a storage in the bottom, then that cascades out. So what you see here is the amphibians, when they hop along the highway, they like to keep their back leg in contact with the curb, and because of that, then you should have a curb that's indented, so it prevents them falling in the gully itself. You got there is a climate tunnel that goes onto the road, so you might have the road might have actually got in the way of nature in terms of a migratory route, and you need to promote that in terms of being able them to go into the road and get from maybe one pond to another pond to live. So it's a climate tunnel, blocking things going on the road, and then green roofs are a methodology of being able to actually promote corridors for insects and things to come into inner city areas, but it's also true of verges and green infrastructure on the side of the road, which can promote biodiversity and connect up different pockets. So therefore it enables the nature to move along the corridor to get to another much larger area.